Today is the 12th session of our lecture series on lightweight hybrid multi-story buildings using new robots. And today the topic is structural design of precast slab systems. And we are very grateful to our Professor Tisan Jayasinghe for conducting this lecture series. It has been a really interesting lecture series, and we have received many positive feedbacks throughout the past sessions. So over to you, sir.
So today we are going to look at, good evening everybody. Today we are going to look at the lightweight slab system and how to design as for zero force. So that's what we are going to do today. So first I will explain the details of the slab system. So, if you take a normal slab, like this, supported by beams. So if you draw a bending moment diagram for this, it will take the shape like this. So that means we get tension here, tension here, tension here, tension here, tension here, tension. Right. Now to take this, resist this tension, what we do is we provide reinforcement. Here we provide this reinforcement. The moment we provide the reinforcement, what is the next thing that happens? This side goes into compression. This goes into compression. Here again you get compression. Here you get again compression. But we know the neutral axis in a column, in a slab of 150 thickness might be at a depth of around 20 millimeters. Now what happens to the rest of the concrete? We say that concrete has cracked. So we don't consider FCT. Concrete in tension, ignore. Why? It is cracked. So we completely ignore the tension carrying capacity of concrete, and we concentrate on the compression carrying capacity of concrete. To carry the tension, we rely on steel. So when we looked at this, actually it's not us who looked at this. This is an idea that we picked up from a system that they used in India. So they have thought, okay, now here it's cracked. Here it's cracked. Here it's cracked. If it is cracked, doing nothing, remove this part of the concrete. Remove this part of the concrete. And we know we cannot remove this part of the concrete, although it's cracked, we cannot remove it. So we actually thought, okay, look at it this way. Now we are going to have a slab. The top surface is intact, but that's the important surface for us. This surface, let's make it thin. But if it's thin, it's going to sag. So put a beam. Here again, it's going to sag because now it's thin. Put a beam. So what we are saying is remove the concrete that has cracked. Why? Number one, it adds to self-weight. Number two, it does provide only protection to reinforcement. It's not doing anything else. It does only one thing, that is provide protection to steel. So let's remove it. And once you remove it, we have a lightweight system. Right. So let's remove it. So Bandhuko, today's lecture is 13 or 12th?
12 lectures.
12th.
Yes.
It is 28th. Page number 1. Civil Engineering Sectional Committee. So let's remove it. So when you remove it, how are we going to do it? And if you look at BS 8110, you can find a section on rib slabs. So this is called ribbed slabs. It is covered well, but the formwork is not that easy. So we thought, actually this is again the system that was used in India that we copied to adapt it to Sri Lankan conditions, because our quality of construction is higher. So we thought, okay, now I'm going to look at it. So you have a beam. I'm going to have another beam. And originally we thought, okay, 1.5 meter spacing. Now these days we consider 2 meter spacing. The original system, the slabs were like this. Three dimension, it looks like that. So the whole idea is we have a slab of like that. The thickness is 75 millimeters here, spanning 1.5 meters, supported on a beam Then we are supposed to add some reinforcement. Link it up. Fill this part. Fill this gap. So the final product is only 75 millimeters of thickness. Later we thought, then further research on this, we found that anyway we have to do a finish for this. To finish this, we need a leveling screed. Why not make it out of concrete? With 10 millimeter aggregates to a thickness of about 40 millimeters. We thought like that. Then it became about 110 millimeters thickness. So this saved a lot of steel. But when you look at concrete, the savings were not great. So later we thought, okay, why can't we do this then? Now, why we needed 75 millimeters was, this was strong enough to complete without any intermediate support. Later we thought us, okay, why are we so worried about the construction stage? We can easily provide a prop here. These are the new developments for the original slab done that. Let's have a prop. Let's have a prop. The moment we go for a prop, we can cast it for 45 millimeters. Cast it for 45 millimeters. And then we can have another 45 millimeters. And an overall thickness of 90 millimeters. We thought, okay, we can do this. Bandhuka, can you understand it?
Yes, sir. It's clear.
Right. Okay. Your sound is little low today.
Okay, I will see, sir.
We can see, he can hear you only faintly.
Now is
So
it
what
clear,
we do
sir?
is,
Okay.
we run this. Right. Then we looked at the modern requirements of Eurocode. We looked at the requirements of Eurocode. And when you looked at the fire requirements of Eurocode, what we found was Eurocode recommends a width of 160 millimeters. Minimum width of 160 millimeters. If it is simply supported, if it is made continuous, you can go for a lesser thickness width. Then we looked at, okay, now the constructability. Then we thought, if you are going to cast this beam in situ, or we precast it, but we have some lifting equipment like a crane or a tower crane to lift the beam, then the weight of the beam is not a major problem. So we thought, okay, let's do this. So we selected, considering that the beam will be in situ cast, we selected a width of 175. And because these are small spans, a minimum bearing of 40 millimeters would be sufficient. But the important thing is, because we have only a small bearing, we make sure the reinforcement continue from here to here. We make sure the reinforcement is of full length, because we don't have a cover problem or anything, because we are going to put concrete here. So we continue the reinforcement to the very end of it. Then we had now somebody might argue, this is the top surface. Somebody might argue, okay, now how are we going to lock it? So we thought, okay, let's have this triangular shaped reinforcement. We can put an 8 millimeter bar or a 10 millimeter bar, and we can have some reinforcement. But when you do this, you will find that this reinforcement is having a lot of cover. Then what we thought was, okay, let's have this reinforcement. And let's have a reinforcement at this level to lock it, and the continued reinforcement to go above it, so it will act as a top reinforcement. So the moment you provide top reinforcement, what will happen to the precast slab? It will behave as a continuous slab. It will behave as a continuous slab. So the shape of the bending moment diagram would be, for live loads, it will be like that. For the dead loads, there is no continuity. There is no continuity for the dead loads. So it will be a bending moment diagram like that for dead load. And for the live load, it will be a continuous diagram. So when you load it, this will have a very satisfactory behavior with minimum deflection. Then we proposed to optimize the amount of reinforcement needed. Now you can see it's a very efficient system because the slab is continuous. And every 2 meters it's supported. It has a thickness of 90 millimeters. Now our aim is minimize the amount of reinforcement. So we thought, okay, let's have a support here. Temporary support. Let's have a temporary support. Now what will happen? While casting, it will behave like that. Because we don't have top reinforcement in the slab, it will behave as a simply supported slab. And these bending moments will be very small, much smaller than this blue color bar. Okay. Now it looks pretty okay. Now our aim is minimize the reinforcement. Why? I'm talking with VAT. With VAT price 350,000. But at the end of the day, somebody has to pay VAT. And when you consider the labor for fixing 1 ton of steel, another 100,000. For not only fixing but the wastage as well. So we are talking about 450,000 rupees. For how many bars? For 272 of 10 millimeter bars. Or it means 420 numbers of 8 millimeter bars. Right. And then we have another requirement called minimum reinforcement. Reinforcement comes to about 0.13% to 1.15%. Now this minimum requirement is also not there. Why? Because we cast the slab like this. We place the other slab like this. We place 2 reinforcement like that. Then we place an additional reinforcement. And can you remember I said that we need a reinforcement for continuity? This reinforcement, the dotted line. So the reinforcement of the dotted line goes there. The continuity reinforcement goes at that place. So this will lock. This will lock. This will make it continuous. So this and then when you are concreting, here you get another one. When you are concreting, what happens? The concrete will fill up all this area. Then if you want to have a conduit, you can run the conduit there without affecting any durability, without having any durability issues. So there is a particular advantage of not using this shape, but using this shape. So this is not good, this is good. Bandhu, can you understand it?
Yes, sir.
Right, okay. Right. So you can see, although it looks simple, I mean, lot of thought process has gone into it. We are looking at every aspect of it. And we are very concerned about the very high cost of steel. We are extremely concerned about the very high cost of steel. So, if you are concerned about the very high cost of steel, now we can look at the requirements. Again with a diagram, little larger diagram. These are only 45 millimeters thick. And then going like that. Then some reinforcement coming like this. So this is like this. So we bend it. So how we make that reinforcement is we bend a reinforcement like this. Then we convert it to this shape. First we bend it in the bending machine this way. This is what you get from the bending machine. At the side we convert it to this shape. Then we arrange a reinforcement here. And in the slot, we'll have a reinforcement like this. Then we have the beam that supports. So the link will do this. And we look at the reinforcement here. And we can calculate the reinforcement. For live loads, it is a flange beam. So all this concrete will be part of the beam. All this concrete will be part of the beam. So we consider it as a flange beam. And we design it as a flange beam. So the beam is designed as a flange beam, but simply supported. So if you want, we can even make the beam continuous, but we can generally consider that the beam is simply supported. But we make the slab continuous this way by having top reinforcement, and the slab will have bottom reinforcement that will come to this level. And to prevent any bearing failure, what we do is we fix a reinforcement here. Good. Then we arrange two H8 bars. Then we arrange H8 bars. And this also can be an H8. And the link can come from H8. So during the construction, we place a prop here. We place a prop here. So it's a prop system during the construction. So we can reasonably say the dead loads, live loads, everything will act on the structure, on the completed structure, but not on the precast members. So we can design the system for the final situation. Can you understand that argument, Bandukha?
Yes, that's clear.
Because if you are having props, we allow the loads onto the structural elements only after the continuity has been fully restored. So because of that reason, without a major error, we can say the whole system can be designed for the ultimate loads, considering that the precast system and in situ cast, everything has been cast in one go. Is it a clear argument, Bandukha?
Yes, sir. Argument is clear.
Hello?
Yes, argument is clear, sir.
Yeah, argument clear.
Yeah.
Because we are considering that we put props. We put props for the beam. We put props for we put props for the. So basically, why we put props? The beam behaves as a flange beam. Because it's all linked properly. But simply supported. Then the slab bears as a continuous beam or a slab. I'll say continuous slab bears as a continuous slab. So basically it's like a beam behavior, but it's a continuous slab of 90 millimeter thickness. So this can be about 300 millimeters. Why? Because the minimum size that we cast this beam is 200 millimeters. The minimum size that we cast this beam is 200 millimeters, but it can be, depending on the span, it can go up to about 300 or even 400 when you have a slab spanning of about 6 meters. For about 5 meters, we can go for this. And so 5 to 6 meters, we can go for 300. And about 7 to 8 meters, we can go for 4. So you can see. So after this, once it's completed, if you don't like this beam scene, we can have a ceiling with Eltero board. Eltero board. So we can have a ceiling here. Then the floor, the thickness, the overall thickness of the slab will be about 300 millimeters. Then how do we support the ceiling? Not difficult. Because when you are casting, there will be a conduits here to provide the tie bolts. So using a tie bolt, and fix the ceiling structure here. Using the same tie bolt that we use for casting the beam, we can use the same tie bolt for fixing the support structure of the ceiling. So the overall thickness of the slab will be 300. Whereas with finishers, any other slab will come to about 200 millimeters. Even if you complete a 150 slab, then you apply the leveling street, then you do tiling. So once you consider all that, it comes to about 200 millimeters. So the cost penalty for using this is the building will be taller by 100 millimeters if you are going for a ceiling. If you are not going for a ceiling, no problem. The beams are seen. If you think having a beam is not a major problem, then you don't need a ceiling. So basically in houses, we can have the beam exposed. But in apartment buildings, because you are selling the apartment, better to have a ceiling. Because you are selling the apartment, then there will be a big task of explaining the people why you have a beam. So it may be far easier to have a ceiling and conceal everything, and there will be a particular advantage because you can do all the wiring before the ceiling is completed, and all the wires will be accessible from below. So if you have any alteration or repair, it's a matter of removing the Eltero board, because Eltero board is fixed by using screws. We don't nail it, we screw it. So because the Eltero board is screwed, any moment you want, you can unscrew it unscrew the screws and remove the board. Then you can attend to all the services and fix it back. What do you think, Bandhuka?
Yes, sir.
It's quite
That will work.
possible. Is that right?
Yeah. Yes, sir.
Yes.
Yes.
So what we do is, now we have a very practical solution, but there is a cost penalty of 400 millimeters per floor. So 10 floors, your building will be 1 meter tall. 40 stories, the building will be 4 meters taller. Not a major problem because it's only 1 floor taller, but we can make a significant saving in steel. Why? Because the beam is precast. There's, it's free to shrink. It's free to shrink. The slabs are precast, so the slabs are also free to shrink. So you can minimize the minimum reinforcement because you really don't need minimum reinforcement. Why are we providing 0.13% of to 0.15% of minimum reinforcement? That is to prevent early thermal cracking and also to take account of shrinkage of concrete. Now we are casting only a small piece of slab. So can you have any shrinkage cracks in such a scenario? Absolutely not. So we allow the shrinkage to take place before we cast the slab. So we don't need this minimum, we don't have to satisfy this minimum reinforcement requirement. Do you agree with me?
Yes, sir.
Bandhugar?
Yes, sir.
Right? So you can see step by step we are optimizing the system. We are optimizing the system. Step by step. Step by step we are optimizing the system. So although it looks very simple, the slab system has been developed with a lot of thinking going into it. So the shape, all that is based on this thinking process. So in that case, how can we design this slab system? So first we'll design the slab. So there are two sizes that we commonly use. This 15 millimeters, 30 millimeters, and this width is 300 millimeters. And the other option is so those are two options. These for when you have a tower crane. Then here when you are lifting manually. Lifting manually. Is that clear, Bandhuka?
Yes, sir. That is clear.
Then we can look at the other advantages. So we have this. Then we apply another 45 millimeters. overall 90. Then we embed marble. This is thin concrete. So we can say we can use marble, terrazzo chips, even 6mm chips. And finish it. The beauty of this system is because there are beams and the overall thickness is precast at 200, then we complete at 300mm, 290. So these are Beam-Slab system. Generally, the delta is pretty close to 0 in these systems. Due to the dead weight. So the deflection is almost 0. So that means we can cut concrete and polish it. Cut the concrete and polish it. The moment you polish it, you can get a very nice terrazzo finish. And then subsequently, say after a few years of occupying it, you might decide, okay, better to have a tile. Tile is only about 8mm. So what is the allowance for finishes? Can be reduced to allowance for finishes will be 0.5 kilonewtons per meter square. And that is the weight of tile. We will not have a leveling street because our idea is level the concrete properly. Because once you remove the shutters, deflection will be 0. Deflection will be 0. Is that clear, Bandhuka?
Yes, that is clear, sir.
That's clear. Right.
Okay.
Now we know the allowance for finishes. Services can be over 0.25. Because in a house or apartment, we don't have a lot of services, but we can make a small allowance. Generally, in houses, we don't make allowance for partitions because we are not going to partition the house. But we allow for live loading. So live loading, the minimum is 2 kilonewtons per meter squared. In any area, there people can gather in a house. Because house will not have a huge number of people, so you can go for a house. But we can use it for an auditorium with fixed seating. Auditorium. In that case, we use 4. On the other hand, we can have a hall. No fixed seating. Then we use 5. And we can also use it for storage. Then we use 7.5 to 10. You can go for 7.5 to 10 kilonewtons per meter square. Then the question comes, can we use it for a storage area? Yes, we might consider a 400 millimeter deep beam supporting these slabs. And we might have 4H16. Then you will find any massive load can be taken. And then there's another trick. You think this can be overloaded. What we can do is this beam we can have another span, but they are cast as simply supported. So at the site, we can make them continuous. So there are many options that are practically possible. And then the other important thing is it's a flange beam. The beam is a flange beam. So we have this. This situation. Can there be a shear failure here? That is why I'm keen to have some lock-in reinforcement at this level. And then some continuous reinforcement at the top. And this is a lightly loaded beam. So the chances of any failure at the face of the beam will be very remote. Generally, it cannot. But if you are designing it for anything up to 5, there's no chance for that to happen. But if you are designing for storage, then better to check it. And how to check it is available as an example on reinforced concrete design for Eurocodes by Moosley and Bungie. And have a look at that particular example. Then you can see how the structural design can be performed. It's a long calculation, but very clearly explained in that book. So if you spend about half an hour, you can understand the logic behind the whole calculation. It's not a difficult calculation, it's slightly long, but you can easily understand if you know how to draw a bending moment diagram for an element. Okay. So now we see what is the design load. Now we see what is the design load. We are looking at the design load. Now look at the design load. The design load, dead or self-weight, 0.09 into 24. Bandhuko, what is the value? Is that right? So this 0.09 means
Correct, sir.
90 millimeter. That's correct, Bandhuko?
Correct, sir. 2.25.
2.2. Right. Now we can compare that with so I'll do calculations on size. 150 millimeter normal slab, our slab of 90 millimeter. Self weight, what is the value here? Then leveling speed, plus tiling. Here an allowance of 0.5 would be sufficient. Here we need an allowance of 1 kilonewtons per meter. So just we keep it as 0.25 because these are apartment buildings, so we don't have a massive collection of services. No partitions, live load 2. Then we have to calculate 1.35 GK, 1.5. So we get 1.35 times 3 plus 1.5 times 2. Manduk, what is the value? About 7. What is the value, Bandhuka?
7.05.
Yeah, so we say 7, okay?
Okay.
This side, we get 1.35 times 4, 5. Is that right, Bandhuka?
Yes, sir. 9.75.
Yeah. So you can see now we make a saving of 2.7 kilonewtons per meter squared. Each floor is 10 floors, 40 floors. For 40 floors, it's about 100 kilonewtons per meter square. So you can see, although it looks small, only 2.7, when you consider a multi-story structure going up to about 30 40 floors. If you adopt this system, you can make a very significant saving on the self-weight of the structure. Is that clear?
Yes, clear, sir.
Anduka?
Yes, that is clear, sir.
So you can see this slab system is particularly suitable for tall buildings. Particularly suitable for tall buildings. We can make, with the lightweight system, we can reduce the load on the foundation by a significant amount. Okay. Now let's see how to design it. So I'll consider a slab of 300 millimeter width, finished 90 millimeter. So we have a continuous beam subjected to a UDL of 7 into 0.3, 2.1. Is that clear?
Yes, sir.
So the
That is clear.
bending moment here will be WL squared over 10. That means WL squared over 10 so that is 2.1 into the span is 2 meters. Two squared divided by 10. So the bending moment is
0.8.
8.4.
0.84. 0.8.
8.4. No, it's 8.4, is it? Two point one, yeah, 0.4, yes, 0.84.
0.84, yes, 0.84.
Bending moment is kilonewton meters. Then how much reinforcement? I'm going to use the shortcut method. MOBD squared. Now we have an important question. Okay. Now we are precasting this element. We can mix concrete at site. And let's say we are using 300 kilograms per meter. So the mix will be 300 plus equals 2500 and we'll have about, so what we can do is we can use an admixture and use about 150 because we are doing a precasting operation, we are not transporting concrete. So we can easily go for a fairly stiff mix and use the vibrate and compact it. Use the poker vibrate and compact it. So we can go for a water content of about 150. So we get X plus Y as 2500 minus 300 minus 100. So 2050.
Yes.
And we cannot use a high ratio because we are compacting. So we have used 10 millimeter aggregates and a ratio of Y over X of 1.5. So I can say 300 plus 820 plus 1230 plus 150 equals 2500. Do you agree with this? These numbers, Bandhuka?
Yes.
Just
Yes,
add
sir.
it and see.
Yeah, correct, sir.
Because I use this ratio and allocate it. So these are the numbers. And if you use good cement, quality cement, meeting 42.5 grade, that might contain clinker, fly ash, blast furnace slag. Any of these things, you will find that because we are using 150 kilograms of per meter cube of water, this can reach about 45 megapascal in 28 days when we compact it well into the shuttle. And we are trying to use 150 or even less. We'll use the minimum water. The moment you use minimum water, we get a maximum benefit. And we are not casting a big section. We are just casting a slab. So the question is, what is the cover? Question is, what is the cover? We are designing according to Euro codes. Now we are looking at the Euro. Is that clear, Bandhuka?
Yes, sir. That is clear.
So the bending moment is 0.84 kilonewton meters when you consider W square dot L, which is the usual value that we use when the steps are continuous. One-way steps are continuous, we use W L square dot N as the moment, design moment. So if that is the case, what is the cover? Now what you have to see is how we are going to cast it. 2 meters long, we lay a polythene. Separate, we first make a perfectly level surface. And how you make a perfectly level surface is, you can have cement stabilized soil. Soil, earth of something like 75 millimeters and compact it to about 45 millimeters. And then we can lay a thin concrete and cut it, or even a rich mortar mix would do. Because what you want is a temper is first large enough to cast these slabs. But we want it to be perfectly level. Otherwise, our slabs may not have a perfectly level surface. So we want it to be perfectly level. So we have to have a polythene sheet as well. And this is 45 millimeters tall shutter, 2 meters long. And you can insert the poker vibrator and compact it well. And because we are manufacturing it as a site, we'll have a say small concrete mixer where you can have 0.5 bags of cement. So you can decide accurately the amount of water needed. Use an admixture, get the maximum benefit of the cement you are using by having a minimum water cement ratio. Reduce the water cement ratio as much as possible. And we can do it because we are using a poker vibrator in a very thin concrete. So we can minimize the amount of water and use a fairly stiff mix. Now we don't need a pumpable mix for this construction. Is it clear, Bandhuka?
Yes, that is clear.
Right. Now, because high strength concrete has a lot of benefits. If you look at the Euro code, you can see durability is under section 4. Durability is under section 4. So we can go up to section 4. Section 4. It gives XC3 as the exposure condition. XC3 as the, just one moment. So here you can see, I have gone to section 4 because the durability is handled under section 4. And I go for XC3 because it moderate humidity, concrete inside buildings and so on. Then what I do is, I'll go to the next table. It says, XC3 member with slab geometry, position of reinforcement not affected by construction process. Now, what do you mean by that? That means, we are going to work on the reinforcement after fixing it. That we often do in normal slabs. But this is a special situation because we are not going to work on the slabs. Because we are precasting this. They are small pieces, 2 meters long, 0.3 meters wide. So there's no reason for us to work on it. Then it says, reduce the class by 1. And sometimes, I might be able to say special quality control. The strength class, if you are using C3545 concrete, it says reduce the class by 1. Reduce the class by 1. So that means we can reduce the class by 1 here, reduce the class by 1 here. So now we go to the next one. We go to S4. Then it says, if you go to S4, you can see the cover requirement is 25 millimeters. But because we are reducing it the class by 2, what is it is 15 millimeters. Is that clear, Vanduka?
Yes, sir. Yes.
So that's how we find the cover. So now we have a section. I'll do a large section. So I'll stop share. So I'm doing a large section. So we need 15 millimeters of cover. We have 8 millimeter reinforcement, and we'll fix another bar. So the effective depth will be, so I'll say it's 25 millimeters. So instead of 15 millimeters, we keep 17 millimeters of cover. So this will be 20. So I can go for 16 millimeters of cover, and I can say 20 millimeters. So the overall slab thickness is 90. So D is 90 minus 20. 70 millimeters. Is that clear, Vanduka?
Yes, that is clear, sir.
Right. Now I can find MOBD squared. 0.84 into 10 to the power 6. Breadth 300. Depth 0.70 squared. What is the answer? What is the answer?
0.57.
Point
57.
0.7.
0.57.
Is it?
0.57. 57.
0.57.
Yes.
Then you find 100 SOBD as 0.57 divided by 4. What is the value? This shortcut method. I'm using shortcut method.
0.1425.
0.1425. What is this? What is this? Vanduka?
29.92.
Sorry?
29.92.
29. Let's say 30.
Yes, 30.
And a 8 millimeter bar has 50 square millimeters. So if we have 2 of these bars, we have a total of 100 square millimeters. More than sufficient. So you can see, when you look at this number 30, we use 7, and our imposed load is 2 kilonewtons per meter squared. So let's see what happens if the imposed load is crowd loading, 5 kilonewtons per meter squared. Let's see what happens if the imposed load is 5 kilonewtons per meter. So if I go back to the earlier calculation, we'll have 1.35 times 3 plus 1.5 times 5. 11.5. Is that right, Mandukar?
Yes, it's great. One.
Is that right?
Correct, sir. 11.55.
11.5, yes. So now we find W squared over 10, that is 11.5 into 2. So what is the bending moment?
4.6.
How much?
4.6.
No, can't be.
Yeah.
Earlier we got 0.8.
4. 0.84.
Oh,
0.84.
sorry. I have to multiply this by 0.3 because the width of the panel is 0.3.
Then it is
Width of the panel is 0.3,
1.83.
so I can't use 11.5. I have to use 11.5 multiplied by 0.3.
1.38.
Because we are considering a panel of only 0.3 meters of width. How much you get now?
1.38.
1.38.
38. Yes.
Then what is MOB squared? What is the value, Bandukar?
0.938.
Sorry?
0.938.
100 days of BD. Point 24 is 0.24. So what is S?
$50.4.
Sorry?
50.4.
60.
50. 50.
Oh, I see. So what are we providing? We are using the smallest bar in the market. And what we do is do this. Then we provide the other bars. Then we place this like that. And also on the panel of 2 meters, panel of 2 meters, we'll arrange a lifting hook about 'll show you how this lifting hook becomes very handy. Is that clear, Bandhuka?
Yes, that is clear, sir.
So we have this. Then what is the continuity moment? The continuity moment will be WS card over 10 here, WS card over 10 here. So then what is the top reinforcement? Top reinforcement will also be same. And we complete it. 45 millimeters. We use an admixture and make good quality concrete so that we can keep about 15-20 millimeter cover at the top as well. Is that clear?
Yes, that is clear.
Yeah. So now we have done the slab. So now we can have the reinforcement diagram. So I'll draw a large diagram for the beam. We have this slab with 40 millimeter bearing. That's the minimum. We're going to have another slab, straight like that. We're going to have link. Like that. We're going to have a reinforcement here, and we'll have a small piece and lock everything. Then we are going to have the top reinforcement here up to a length of 0.6 meters. This is based on the simplified curtailing rule, where we say the top reinforcement can be curtailed at 0.3 times L, where L is 2 meters, so we can curtail it at around 0.3 times L. And all these reinforcement will be H8 at 150 center to center. Both top and bottom. So we get a very strong slab, but lightweight. When you have two numbers of H8 bars over width of 300 millimeters, where H8 bars are spaced at 150 center to center. Now you can see even the crowd, not only the crowd loading, even the storage loads can be carried by this slab. But you have to pay a penalty by either having lot of reinforcement here or by increasing the depth of the beam. Either increase the depth of the beam or increase the amount of reinforcement in the beam. So I prefer increasing the depth of the beam. I prefer increasing the depth of the beam. And the width of the beam will remain 175. So this gap will be 75 millimeters. No, 95 millimeters. That will allow us to fix this reinforcement very well. Is that clear, Bandhuka?
Yes, that is clear, sir.
Great. So, this is a trap system. Then depending on the span, in a similar manner, considering it as a flange beam, we can design the beam as well. That we'll discuss next day. But today I explain in detail how we arrived at 45 millimeters. Why it is sufficient because the slab cover requirement is only 15. And why we had to use admixtures and go for high strength side mix concrete when you are doing the precasting operation. So this a very significant cost savings can be made versus the traditional systems. And even for a 6 meter span, what becomes larger is the beam, but not the slab. Slab will remain the same of 90 millimeter thickness and continuous over every 2 meter, where there will be either a wall or a slab. So we can, the other beauty is we can directly support this on a wall. We can directly support this on a wall. So we can make it load bearing. Some of the walls can be made load bearing. Some of the slabs will be supported on the precast beams. So generally when you have 90 millimeters over 90 millimeters slab over 2 meter, shear will be minute. You don't have to worry about shear. Is that clear?
Yeah, now.
Yes, yes, sir.
Then shall we take the questions?
Yeah, yes, sir. There's a question. Is there any special slab arrangement under the partition walls, either in X or Y direction?
Actually partition walls, it's not a problem at all. Because if you have a slab, beam, and another beam, If you are not sure of this capacity, but the beam has to be designed for the partition load. We can have a small concrete lintel and do the partition. Then the loads will be transferred not onto the slab, but onto the
Beam.
beam. But when you are designing the slab, the requirement is, if you apply a concentrated load here, 40% will be carried by this, 30% by this. That is how it goes.
Okay.
Okay, Bandhuga?
Yes, clear, sir. And the other
We can
question
have
is,
this, if you have any concentrated load, you can consider that only 40% of the load is taken by the slab supporting the load, and 30% will be distributed to the slabs on either side. So three
okay,
slabs will share it. So the total width of the slabs will be 900. So you'll find it is a very efficient system.
okay, sir. And the other question
Any other
is,
question?
yeah, when reducing the slab thickness, there are other concerns like when reducing the slab thickness, there are other concerns like fire rate requirement,
Yes.
heat transfer,
If you have any
contamination.
worry about fire rating, because this is a slab, so half an hour fire rating is enough. Because if it is a slab, we have to evacuate the slab, right? Even if a slab has a local collapse, the whole building is not going to collapse. So what we need is about 30 minutes fire rating, and 30 minutes fire rating can be easily provided by these slabs. And if you have any issue with fire rating, then what you have to do is apply a seal. Sealing will look after that. Is that clear
Okay,
answer,
sir.
Madhu?
That is clear, sir.
Yes, sir.
And then can we use precast slab and beam for washrooms and slab or roof slab?
Like
Like that?
Precast slab is very good because on top of that we have a street, high quality street, not just the normal concrete. And then because design pieces, you can easily have a washroom up to a width of 2 meters as with precast slabs. Okay?
Okay, sir. And there was a question at the very beginning. As I just sent one photo to the chat box, sir. That distance is asking from the sketch we drawn earlier. That here also
Yeah. What's he asking?
that bearing distance for the panels.
A bearing is, we have proven with the testing. 40 millimeter bearing is the minimum, and anything more than that is more than sufficient. Can you remember? We have put two reinforcement here. That is to cater for. We put a reinforcement here. We put, and then this is a reinforcement. So because of that, there's no bearing issue.
Okay, sir.
So we have designed the beam for shear, flexure, and all that. So here the main critical item will be the beam, not the slab. Slab has more than enough strength. The issue is the beam, so we have to properly design the beam.
Okay.
Is that clear?
Yeah, that is clear, sir. And last question was, I think
Any other question?
he's asking about the space between beams.
Space between?
Beams.
2 meter.
Yeah.
Maximum 2 meter.
Okay. I think.
So every 2 meters you have to have a secondary beam, which is span onto primary beams. So the primary beams can have any span, 4 meters, 5 meters, 6 meters, 7 meters, 8 meters. So what you have to do is increase the depth of our beam if the span is large.
Okay, sir.
Yeah.
I think yes, clear, sir. Questions are that was the last question, sir. Actually, now one more question is there.
Sorry?
One more question is there, sir. What about
What
the
is that?
reinforcement covering? As it less covering than 20 millimeter, will there be any issue with the durability?
No, I mean we are selected 15 millimeter as the minimum according to Eurocode. Because we are using high strength concrete.
Okay, sir.
And this is a very high strength concrete compacted very well. And we can easily cure the steps because after about 24 hours you can make it vertical and then carry it.
Okay, clear, sir.
Okay?
Okay, clear, sir. And that's all I think questions.
Yes.
One more question is there. Is imposed load to enough since the above slab load is acting during the casting?
No, casting we have a prop.
Yeah,
That's
we are
why I
transferring.
said mathematically the whole system is on props as long as we are casting. So we can, without a big huge error, we can reasonably assume that everything is cast monolithically and we can design the reinforcement accordingly. Is that clear?
Yeah, that is clear, sir. So there's one question asking whether we can use pre-stressed beams.
Yes, yes, if
Oh.
you can, but you know these are low technology systems done with high technology, like high strength concrete. But we want to make sure without any investment, without a big investment, you can cast the slab on ground. That's why we don't go for pre-stress, but pre-stress also can be used.
Okay, clear, sir. Today, okay, sir.
Sorry?
Okay, sir. I think questions are over there.
Good.
What shall be our next session?
Sorry, in the next session, we'll discuss how to design the beam.
Beams.
Okay?
Okay. Thank you very much, sir. Today also, it's a very interesting session. And
Yes.
I would like to invite Vice President ISL, Engineer Mrs. Kamala Gunawardana to do the vote of thanks. Over to you, madam.
Oh, sorry. Can you? Yeah, I think I'm audible.
Yes, we can hear you.
Okay, yeah. I think, as usual, I think I got this opportunity to give the vote of thanks, actually, every day, every week, I think we are coming to you, Professor. So we are listening to your lectures, and of course, today I joined at the last few, like 30 minutes. So we were coming from the ISL. So I think our members who are joining these participants, I think you all are really lucky to follow these courses. And thank you so much, Professor. This every time you get some new idea, new concepts, if you say, those are related to something, right? This is we are doing for this. If you get this topic, structural design of continuous reinforced concrete beams, flanged beams. So something, or I think if you get it as CPD hours, it's really very much meaningful things our participants are getting. And recently when I think when someone went to CB training, I don't know whether you know that, the supervisors have told them to follow your lectures, right?
Right.
So we are very happy.
Yes, many have said that. Yes.
Yes. Bandhu is the one who gave me that message. So I told it actually today. I met someone, president. I had the CPD meeting today at the ISL. So I have been encouraging everyone because this is a marvelous, and this is your, even today there was a lecture from very known persons about the corrosion. Even there we mentioned it actually. So really you are doing a great job, Professor. We never ever forget to this devaluate. I actually really appreciated that Bandhu gave me the opportunity to thank you, because I
Yes. Okay.
normally
Thank you.
welcome you, but thank all the participants. Thank you so much for your enthusiasm and your encouraging questions. And Bandhuka, you are doing a marvelous job. So coordinating everything like I did previous time, better than you do better than that. So with all that, I think we'll wind up the session. Thank you so much, and I thank all the secretariat people and those who are behind us, those supporting us, for everything. So thank you so much, and have a good day. Good night.
Okay. Thank you, madam.
Thank you very much.
Thank you, sir.
Okay,
Good
I'll
night.
leave Bandhu.
Okay,
Right?
sir. Okay. Good night.
Thank you.